Hello there.
Hi, Enrique.
Thank you for joining.
Hello.
So let's give a couple more minutes for people to join. So today we are going to, we had to make a slight adjustment to the topic, but we are changing from LM information extraction to fine-tuning transformer model using Hugging Face. And uh, so let's see how it goes. We will start. So the idea is similar to last week's session, but last week we did something using PyTorch directly, and this time we are going to use Hugging Face. For those of you who are not familiar with what's Hugging Face, it is a very handy Python library that allows us to train initially transformer models. So these are language models like BERT or GPT, and these are the precursors to what GPT-4 and Llama are. You can actually think of them as the same technology, but at smaller scale. And there's a wide variety of those. Today we're going to be looking at one called T5. I like T5 because this is what started with the revolution of prompting. So prior to nowadays, you hear about prompt engineering, but prior to that, the AI tasks were more like, okay, we have specific model trained for machine translation from English to German. So whatever you pass this input, it will always come out as the German translation, or it could be a sentiment classification, or like any structured task before that had its own specialized variation of the transformer network. With Flan, what happened is that the researchers in Google started figuring out that they could train the network to perform different tasks, and they can condition what tasks they want based on the prompt. So they were giving instructions, and so you could ask for a translation, or you could ask for converting um, uh, any type of operation, like classification, where you can tell like these are the classes that I'm looking at, like a positive review, a negative review, and this is the text of the review, and it will tell you either positive or negative. So the different NLP tasks started becoming or reducing to prompting. So the prompt is instruction, and the context is the actual input that you used to pass to different models before. So this set the stage to making neural networks that have higher number of parameters, uh, all the way to what we have today, which is Llama 3.2, 300 billion parameters, or GPT-4o, or whatever else. They're trained to follow instructions using prompts, and pretty much you can do anything that you can imagine. I'm not saying that it's going to do it well, but you can get creative and try to find your way around building AI applications by doing careful prompt engineering. So T5 started all this, and Flan is just the specific version of T5 that follows instructions. So what we are going to do today is just download a toy data set of instructions and try to fine tune a non instruction tune based version of Flan to see what we get out of it. And I found this blog post. So we're gonna just follow this on Jupyter Notebook on the HPC and see how far we can get. Please feel free to ask any questions. And yep, so let's get started. So we're gonna ask for 1 hour. We want 8 cores, 8 gigs of RAM. Let's see if we can get away with V100. Okay, so hopefully we'll get it soon. Let me just log in to see what's the occupation. It looks like there's a space, so hopefully we'll get it soon. But meanwhile, we can perhaps walk through the tutorial. Yes, this is what I was mentioning. This Plantify is the precursor to the modern conversation-abled LLMs that we have, but we can also do text classification. We can do any sort of generation. We are going to use Hugging Face, the Transformers library, and some companion libraries like datasets, tokenizers, evaluate, and LTK. Um, let's see if we can request another one. In Puma. No, in Ocelot. So just to give you an idea of what is the current occupation, oh, okay, we got one already. Anytime you use the HPC, you can use the nodes PC command to see what is the current status. So there are plenty of GPUs available on Ocelot. Let's see in Puma. Yeah, there are a few as well. Many of those are buying nodes, but it doesn't matter. So we got one in Ocelot. We can get started there. Let me share my browser again. Let's connect to Jupyter. By the way, is the font size large enough, or do you want me to increase it?
Looks okay to me so far.
Great, thanks. So I'm gonna break down or separate this, and I'm going to share my screen differently, such that we can see both windows at the same time. And hopefully this will make it clear. So we need to do pip install LTK. It says transformers, equalizers, value, Oh, score sentence is based on. This hopefully won't take long, but I can tell you what. Maybe let me make this larger. Okay, so LTK's library that was popular prior to the deep learning tsunami to do NLP applications, but it has some cool utilities like tokenization or implementations of metrics, text cleaning stuff. So it comes handy to have it installed. So it can take care of also lemmatization, etc. It is not trivial to do it, but it's taken for granted when we build AI applications nowadays. Datasets is a library by Hugging Face as well, and it's really cool because sometimes people just post their data in a structure format that we can download again, and it's really usable for us. We don't have to do any transformation or loading data. Instead, it's used as if it was a data frame, pretty much. Transformers, that is the backbone of Hugging Face. Tokenizers is a utility, a fast utility to break down strings into words. Evaluate contains some metrics by Hugging Face. Row score is one metric that we are going to use. Sentence piece is a utility to tokenizers, and Hugging Face Hub is a utility that we use to actually download stuff. So let's portal this, and hopefully it'll work without crashing. So we're gonna import basically all of those. What is noteworthy here is that we are importing the T5 associated classes. We have a tokenizer. The reason for this is that each model has its own algorithm to split the strings into words, because they are learned by the data, so they don't really split by word itself. Instead, they find subwords or pieces of words that are frequent enough that they're shared, like prefixes or suffixes. And we don't hard code that. Instead, each model is done with a different algorithm. So there's always a companion tokenizer for each model. D5 has its own. There are some special tokens that indicate when a sentence ends, or when the input starts, or what is part of the instruction and what is part of context, and so forth. You, as a developer, don't have to worry about it. The tokenizer is going to insert all of it for you. This is a utility function. Then we have a specific type of transformer, D5 for conditional generation. So this is just the transformer with a configuration such that we can generate text out of it. And this is a training, the training utilities. We're going to train not by ourselves. We're going to use Hugging Face's utilities. So it works. Let's move on. Plan T5 is actually not that small, so it has, there are several versions. For example, recently I worked on a research project in which we fine-tuned T5 base. It requires 1 gigabyte of video memory, but it should be enough on the server that we got. So we need to specify the model name. We're starting to use Hugging Face here. Model name. So we want to refer to the model by its identifier on the Hugging Face repository or Hugging Face Hub. Here is Google/plan D5 face. So I think that this is self-explanatory, but what it means is that there's an organization. This one was developed, ergo hosted by Google. Then we're going to load the tokenizer. We're going to use T5 tokenizer from pre-train. What this does is that it goes to the hub and it downloads the tokenizer for us. So we don't have to have it ahead of time. It'll be done for us and it will be cached. So you can see all these files that were downloaded. So some configuration stuff in the actual data files. If we do it again, it won't print anything because it's already cached on the local file system. And this is the same paradigm when dealing with Hugging Face. We're going to do exactly the same, but for the model. And then there is a data collator. Let me type it and then I'll explain what it is. And now you can see that we're downloading 1 gig worth of tensors, safe tensors. This is the actual model file itself. It is the base model, so it's not the extra large nor the small. And a data collator is just a utility that comes handy when training. The reason for this is that when you're training neural networks, you want to batch your inputs. So a GPU is really fast on calculating stuff. So we cannot just like pass one by one because most of the time is going to be wasted by moving data back and forth the GPU to the CPU. Instead, you want to create a batch, submit it, because everything that happens for the same batch will take the same time as if it was a single input, as long as the batch fits on the memory. So you want to maximize the amount that your throughput, and that throughput is going to increase if you're able to accumulate extra inputs. But the issue is that you don't know if your prompts have the same length because you may be asking a different question or you may be providing different content. So there's a way to add padding stuff and then slicing everything together and packaging into batches. The data collator takes care of that for us. So that's something else about Hugging Face, that if you were using PyTorch directly, you have to deal with it yourself. So we have now the tokenizer, the model, and the data collator. So we need the data set. So we're going to copy this. This is a data set by Yahoo. Excuse me. And it's the same thing. We specify the name and we download it. The load dataset function, it's another utility by Hugging Face that connects to the internet. Let's say just here, and downloads some data, but it's able to actually message the input files into the format that we need. And that is what it's doing right now. So this is the dataset published by Yahoo, but it's not in the format that T5 expects. But somebody put in the actual code to marshal it to the shape that we need, and it's done here. And then we can actually take a look at it. So Yahoo Answers Q&A. This is a data set that contains 87,000 elements. And we only have a training data set, so we're going to split it in a bit. But we have a question, we have an answer, and some extra metadata. What's the category of the question, and what are best answers? I'm not sure exactly what it means, but we can actually inspect it. So we are going to follow the blog post and make a split. So we need a testing split to evaluate after training. So let's see. Yahoo Answers QA is since there's a train. So look at this. This is a dataset dictionary. That means there is a key and a dataset as a value. The key is train, but we want a test one. So the datasets from Hugging Face already have these utilities that sample randomly and give you a proportion of the specific amount of data in as testing. So let's do it and see what is the difference here. So now you can see that we have, in addition to train, we have test, but the number of rows was reduced in training. So if we add these two quantities together, they should be the same. So what if we want to see how does one of these data points look like? So we can do QA, test, select. Let's just look at one. We want to see the question and the answer. Okay, so there you go. Let's do it this way. Yeah, sorry about that. Yeah, this should work. I don't know where this come from, but let's just select one randomly here. So deep poll, I guess that it's some sort of legal procedure that you have to do somewhere. I'm not really familiar. But this is the type of data that comes from the Yahoo Answers QA. This is similar to Reddit. I don't know, like if you've been around long enough, yeah, Yahoo QA was a big thing probably 10 years ago. But nowadays, this could be like Quora or Reddit. So what we're going to do is that we're just going to fine tune T5 on these questions and try to get T5 to behave like it. So as I was mentioning, we need to provide an instruction, and here we need to define that prefix. So our custom prefix is going to be please answer this question, as if you were prompting the model itself. And then we need to marshal the data to that shape. So for that, we're going to use this specific function. And it seems that there is a mistake here. So let me see. This is just indentation. Let me copy here everything. I'm going to explain it line by line. What we want to do is that we want to take one example, like the one we have here in the 18th cell, and we want to change it from a data frame into a string that we're going to feed into it. So the way to do that is that we are going to take all the examples. So we're going to create a function that takes all the examples that we provide. Could be training, could be testing. And we're going to get the question out of it, but we're going to prefix it with this prompt. So this could look like, if you were running it on this input, it could look like, please answer this question, colon, space, how do you change your name by did poll? And then that becomes the inputs. So once we have the inputs, we need to tokenize it using the model's tokenizer, and we'll get certain numbers that represent the codes in which each individual word corresponds to the dictionary of the model. And then we want the output. So the output is the answer, which is this specific sequence. So if we prompt T5 with, please answer this question, column, whatever goes in here, it should give us this as an answer. It should generate that, or we call it on NLP, it should decode it. So that is what is happening here. We don't need a prompt for it. Instead, it's just going to be the output, and we're going to tokenize it too. That means that we provide the input codes for the questions with the instruction. We get the output codes of the answer. So then we put everything together into a dictionary and we return it. So let's see what happens if we run this on this specific input. So let's go one step further. So X input. Well, input. So this is it. So far so good. We want to see the IDs. Pardon my flakiness typing. These are the codes that correspond to it. So I'm just gonna erase this. Once we have it, like we applied it for a single data point, but we can use Hugging Face as well to map it to the whole data set. So and we're using the batch true function. What this does is that it dispatches everything into these different courses we have and applies it in parallel. So it is optimized in a sense, and that saves us a lot of time. So it'll take about 30 seconds to do the training split, and then perhaps a little bit more for testing, 10 seconds. So the result of this cell is that we have a data set pre-processed on the shape that we need for training and evaluation. And to evaluate that, what we need to do is that we need to instantiate the metric function that is called rogue. For that, we're going to use, it's already done for us. So this is also data driven. So somebody has this Puncty model and we have the rogue metric. So what it does is that it sorts of, we cannot change this, like we cannot do string matching because any specific variation is going to trip that. Instead, we're looking for lexical overlap, and rogue is a metric that is done for that. So we're measuring how many subphrases are included on the generated file. So perhaps if we're missing a dot or a comma, or if we just change a word by a synonym, it won't be penalized because Rogue is smart enough to do that. Then we need a function that applies this metric and computes it for us. I'm just going to copy it and paste it here. And I'm going to explain it line by line. What this function does is that it takes the output of a model. We haven't run it yet, but let's assume that we have one specific output. And part of it is going to be the predictions, which are the tokens generated, and the ground truths, which are the tokens that come out of the answer in the dataset. And is going to decode it. The tokenizer means the decoding means that we take those IDs, such as these ones, and we map them back into the words that came out. We don't have to worry about that because the tokenizer already handles this. It decodes the generations and decodes the ground truth. So let's just change here. I think that this is easier to understand. You don't have to worry too much about this. What this means is that sometimes it pads the outputs when they're short and they're not long enough to get to the batch length. We're removing those elements out of it using NumPy. These are ground truth. Similarly here, we decode them. There are some special tokens added, so we are skipping them because we don't care about them. And then we're using LTK to split by sentences. So we are splitting them, and then we're computing rogue score over those. The result is going to be a single number. The closer it is to 1, the higher. The closer it is to 0, the worse. So we're going to define it, and this is one of the building blocks before doing training. Once we're doing training, we need to define a set of hyperparameters. We're just going to copy them and paste them. I'm going to try to go a little bit faster because we need enough time to train stuff. But we got the learning rate, the batch size. So our batch size is of 8 sequences. This might look rather small, but unfortunately, like when you take a single string, you split it into subwords using tokenizer. So you could have, I don't know, 500 words in a single sentence. Then each of those is going to become a vector that has 784 different components. So it becomes a cube. So you can visualize the tensor as a cube. And since each number is a floating point number, it starts to gobble a lot of memory. Therefore, we need to keep the batch size small to fit into the GPU. So there's also a batch size for the evaluation, weight decay parameter that is going to decrease the learning rate as we advance. So it's going to be aggressive at the beginning, but then once it picks up part of the patterns, that learning rate decays based on this coefficient. How many epochs do you want to train? Here is 3, and the total number of checkpoints that we want. So here comes the magic of the training procedure. We save everything as the arguments, and then we are going to actually train it. So let me paste this here and fix this. Pip install accelerate. So accelerate is another utility that allows us to use the GPUs. So if we had 2 GPUs available, it could do it as well. Like accelerate could use them automatically. Let's see if it works now. So we'll have to restart the kernel. I'm not sure why it takes so long to import stuff. But one of the nice things is that once we download stuff, we don't have to download it again. Once we pre-process the dataset, we don't have to spend time doing it again. Well, maybe we do. So I take that back. But usually, depending on how you configure stuff, when you apply an operation, it saves it into the disk, so you don't have to repeat it again. I'm not sure exactly why it's not saved this time. Okay, so now it did work. So something important here on the training arguments is that you need to provide an output there. All your artifacts, meaning the copy of the model that is being trained, is going to live there such that you can load it later on. And we're going to evaluate each epoch. So once we have those arguments, the training arguments, we can actually create a trainer. There's a particular type of trainer called sequence to sequence, because we take an input sequence, which is a question, and then we generate the answer, which is another question. Many problems map to this. So it could be dialogue, like conversation, could be machine translation from English to German, or could be question answering, such as this. So if you can map your specific task to the abstract concept of sequence to sequence, then you need to use a trainer such as this. We are training T5. These are the arguments, and we're specifying what is the training data set, what is the evaluation data set. We specify the tokenizer, the data collator, and the metrics. So you set everything to train. And finally, we just call the train method. And then this is going to start the loop. And let's see how long it takes. So it's going to take a little while. We only have 20 minutes left. So I don't want you to get bored looking at it because it's going to take 1 hour and a half to the 3 epochs. But you can see here, what I can tell you is that at each epoch it generates this table and it gets updated. So by the end of epoch 1, it will tell us what is the training loss and what is the validation loss. And if we go back to here and we connect to the shell, let's see if we can see how the GPU is being utilized. So NVIDIA, let's see. So this command, this just gives us a snapshot in time, but we can repeat it each second to get like a task manager view of how we're using the GPU. So we are using 14 gigs of RAM. This includes the model. So one of the reasons why it uses so much memory is that the model itself is 1 gig. Then we have the gradient. Each parameter has, besides its own value, that's its gradient value associated. So we duplicate the amount of memory that could be 2 gigs per model. And then the trainer uses an algorithm called Atom, and this has momentum. So momentum has another 2 copies of the parameters. And so that blows up the budget of memory 4 times. So if you're training a model that uses 1 gig of RAM, then we're actually using 4 gigs to store its parameters during training. Then we have the batch. As I was telling you, it blows up. So the batch is large enough to fill up another 9 gigs of RAM, and we get to this. So perhaps we could feed another sequence and have batch size of 9. One strategy to mitigate the small batch size is to do gradient accumulation. So that means that we do multiple forward passes, and once we compute the gradient, we accumulate it. We add it together before applying one optimization step. This has theoretically the same result as doing a larger batch size, but it takes 2 steps before applying the optimization step. So it'll take longer to converge to the same result. What is important here when you're training networks such as this is that you try to maximize the GPU utilization. Should be ideally closer to 100. Because when it's not closer to 100, it means that the GPU is sitting idle, and then there's something else happening, like you're probably pre-processing the data or moving data back and forth the GPU and the CPU. And you don't want to do that. You want to keep it busy while you're doing other stuff. And also use as much memory as you can. So that is important as well. So these GPUs, the P100s have 16 gigs of RAM. If you're using an H2, the latest one there's a version that has 80 gigs. And there's one that has, I think, closer to 100 gigs. So you can train significantly larger models. So we could probably fit T5 XL. So let's see how it's going here. It has done 1,000 steps. So it means that it has taken 8,000 input questions and answers and trained on them. But it's going to take a little bit. So yeah, I think that's the extent. So we're going to get into this because we only have 15 minutes. I'd rather allow you to ask me some questions if you have. And I will post this video into the website as soon as it's available. So the closing remarks are that if you're using Hugging Face, it is relatively simple to train a transformer network or any neural network if you have a trainer available. It is like you don't have to do low-level coding such as we did in the last session. So it is nice if you're working as a researcher on AI. Hugging Face is now the de facto programming framework that you use, and people share their models from Hugging Face. So it's a really useful skill that you have to have. And yeah, that's it. So do you have any questions?
I had a sort of very general question. I'm quite new to this whole universe.
Mhm.
Can you give me sort of an example of once you've trained this model, is this going to be something like a large language model where you could then ask it questions and it would give you information based on this particular Yahoo Q&A data set?
Yes, pretty much you nailed it. The
But
difference are
go ahead.
that if like an LLM such as GPT already has a lot of background knowledge baked into it. In this case, there's going to be some, but the way it's trained is meant for you to add the specific context that this, well, not necessarily, because this data set already has the answers.
Yeah.
So it'll be constrained to the type of questions that you would see on Yahoo Answers. So you could technically train it on Reddit, but the party trick, and I'm not meaning this on an insulting way of T5, is that you can train a single model to do a lot of tasks in which you control the task by the prompt. So it is not T5 is not meant to be a chatbot. It is meant to be a translator or a summarizer or a question answer machine from a knowledge base.
Okay. So this is a very sort of specific, constrained large language model, sort of.
Yes.
Yeah.
And one of the advantages of smaller LLMs such as this is that you can run it on your own computer.
Yeah.
So we're using right now the HPC in a single GPU. The P100s are old. So just to give you a sense of that, on my own personal computer at home that I use to play video games, I have a 3090 Ti that has 50% more RAM, and it's like 3 times faster than this. So I can run it myself too.
Yeah.
But I could never run GPT-4. You need a cluster for that. Like we need to use all the GPUs on the HPC, and I don't think that it'll fit. So you do a trade-off. You lose some flexibility and generalization capabilities, but you can actually run yourself and save the money. You don't have to pay for API access or something like that.
Yeah. Nirav was talking to me a couple of weeks ago about building class sites where they just put in the course materials, and then is that a similar sort of use that so you end up with a model that's based on the materials for a particular class, and it doesn't have all the other stuff, but what you want the model to do is have the information for that class.
So what you're referring to is an application of RAG. So RAG means retrieval augmented generation, and it's fun. So the end goal is exactly what you said, but the approach to do it is a little bit different from what we're doing today.
Okay.
In the sense that we're training the network to give you the answers. In RAG, you don't train the network. Instead, you use it as it is. It has already been trained on something else.
Okay.
But in order to give it context, since it hasn't seen Yahoo Answers or the course material, you do a prior step in which you retrieve the relevant documents from which the question can be derived. And then you show it to the LM, like, Jake asked me this question, read this book, and give me an answer based on what you read.
Okay.
So you can achieve that using LLMs as well. And that gives us the flexibility of being able to deploy it for different courses without having to do this for each individual course.
Thank you. Thank you. It was very helpful.
Of course. Okay, so then if that's it, then I will call it a day. So thank you for joining, and hope that this comes handy. Like if you watch this video after it's posted, please send me an email if you found this useful. It's nice to know if people use it. Of course, Jonathan. All right, so I'm going to stop sharing here. And I'm going to stop the recording. So thank you and have a nice weekend.
Thank you, Enrique.